What if the most elegant equation in physics wasn't E equals mc square, but P equals cos square theta? This deceptively simple formula describes the strange reality of quantum mechanics. It tells us the probability that a single photon, a tiny particle of light, will pass through a simple filter. But why the cosine and why the square? This question forces us to trade our everyday reality for the abstract world of linear algebra. In this video, we are going to break down the most foundational experiment in quantum physics, and you'll discover how quantum states are represented as vectors and measurements are nothing more than vector projections, how the Bond rule converts the projection into the observable probability. So, before we dive in, let's establish a context of what we should know before advancing. Current computer systems are based on Boolean algebra and binary arithmetic for information processing, where a value can exist in only one state, being either true or false, while in quantum computing, information is processed using a qubit, which can exist in a superposition of both states, allowing for a continuum of possibilities until it is measured. Now, we will learn how linear algebra helps in modeling the latter information processing system. For discussing why quantum computing and quantum mechanics needs linear algebra, let's look at a very simple setup with an LCD monitor which only emits light of one color or frequency. And the light emitted by this monitor is polarized linearly, which can be tested by placing a polarization filter in front of the detector. Now, if the filter is oriented parallel to the screen, nothing happens and we can still see the light. But once we start rotating the filter, less and less light is transmitted until we arrive at the rotation of 90 degrees and no light comes through at all. Now, for experiencing the quantum mystery, let's rotate the light source to an angle of theta, say 45 degrees. Also, let's take the liberty to send the light in its tiniest unit, photons. On doing so, our detector shows that roughly half the photons gets through and half don't. But here's the kicker. For any individual photon, it does not get halfway through. It either makes it to the detector completely or it is completely blocked. It is as if the filter forces the photon to make an instantaneous choice. Do I pass or do I fail? This is the core of quantum mechanics. A system exists in a superposition of possibilities until a measurement is made, which forces it into a single definite state. You might be thinking this is just polarization of light. How does this concern linear algebra? And here's the catch. To understand the strange behavior of photons, we need a mathematical language, and that language we'll conclude soon. Instead of thinking polarization as a wave or a simple arrow, we think of it as a vector in a 2D space. Now, let's define a horizontal polarization state as a basis vector, say kth, and also a vertical polarization state as other basis vector, say kv. And let theta be the angle representing the current state, deriving the current state vector ket phi. This gives us the state of photon at an angle theta, which is represented as phi vector, which on further solving gives phi ket as the cosine and sine of angle theta in two-dimensional space. Now, having a closer look at ket phi, we can see the resemblance to linear combination of two vectors. And in our setup, the polarization filter is testing for the horizontal state kth, and an interesting thing can be noted regarding the probability of a photon passing or not, that it is found by taking the dot product or the inner product of the photon's state vector ket phi with the filter's state kth and then finally squaring the result. This is also known as Bond's rule. In geometric terms, this inner product of kth and ket phi is simply the projection of photon's state vector phi onto the filter's measurement axis h. It is the shadow of phi vector casted on the horizontal axis. The square of the projected length, which is cos square, gives us the probability of observing the photon in the horizontal state or passing through the filter. The famous cos square theta relationship is Malu's law, but now we see its quantum foundation. The amount of light that gets through isn't just a wave phenomenon, it is a probability that an individual photon will be projected into the state defined by the filter. This perfectly explains our experimental result. With these, we have enough evidence to model the mathematics for quantum world, and the answer is obvious now that it should be linear algebra. From our experiment, we can take the quantum states as vectors and their linear combinations, and the measurement of the physical quantity is best represented by matrices or linear operators, which solves the discreteness problem of the quantum world. Before we move on, let's discuss about the notation that we have been using like these in the screen for the horizontal and vertical polarization states. But what do these symbols really mean? To describe quantum states properly, physicists use what's called direct notation or bracket notation. A kit like phi here is just a column vector. Since our photon can be in any mixture of horizontal and vertical polarization, its state vector phi is a vector that lives in this 2D space. The horizontal axis is the basis state H and vertical is basis state V. It tells us how much of the system is in each basis. Here, alpha and beta are called the probability amplitudes. As represented here, if the state vector is closer to kate V, it collapses to vertical axis after the measurement, and if it is closer to kate H, it collapses to the horizontal axis. If a kate is a column vector, then a bra is its row vector version, and it is defined as the conjugate transpose of kate phi. This means we flip the column sideways and take the complex conjugate of each entry. Now we arrive at one of the central mystery of quantum mechanics, the Born rule. We already established that the inner product bracket pair of h and phi gives us the projected length cos theta. But why do we have to square this number to get the probability? The reason lies in mathematical requirement for quantum states. A state vector must always be in a unit vector. Its total length must be always exactly 1. This is called the normalization condition, which is expressed as bracket pair of phi is equal to 1. And it simply represents the fact that the total probability of all possible outcomes must add up to 100% or 1. And this is the quantum equivalent of saying the photon must exist in some state. In our 2D space, this means the sum of the square of the horizontal component alpha and the vertical component beta must equal 1, just like the Pythagoras theorem. Since the amplitude bracket pair h and phi is alpha or cos theta, by squaring it we get alpha square or cos square theta. This operation converts the abstract complex amplitude into a real number between 0 and 1, which is the only way a mathematical result can be interpreted as a physical probability. You might notice that in our example, cos theta is a real number. That's because our simple polarization space is a simple real valued slice of a much larger complex mathematical space, a Hilbert space, where all quantum states truly exist. Squaring the magnitude is one rule that applies to all of them, complex or not. To prove that our abstract math works in the real world, or at least the simulated world, we turn to code. We will use the Python and the NumPy library, which is built for handling vectors and matrices. First, we define our measurement filter. The horizontal and vertical polarization axis, kth and kv, they can simply be defined as the NumPy vectors 1, 0 and 0, 1. And state vector h is the state we are checking for. Then we define the function to calculate the probability of proton to be passed at certain angle. Next, inside our function, we define the photon's state kate phi. Based on the input angle theta, we calculate its component cos theta and sin theta and store them in the phi vector. Note, we convert the degrees to radians as Python's math library expects angles in radians. Now comes the moment of projection. The quantum inner product bracket Kate Yachts and Kate Phi is implemented using the dot product in NumPy library. This single line gives us the probability amplitude that projected length cos theta. To get the observable probability, we apply the Bond's rule. We simply take the amplitude and square it, giving us the final theoretical probability pH is equals to cos square theta. Here, as in sample uses, we have inputted the angle of the orientation of the filter and printed out the probability of the photon to be passed. And in this uses, the angle we have inputted is 30, and the probability of the photon to be passed to the filter is 75%. The theoretical number is great, but physics is about reality. So, how does one photon choose to pass or fail? We run a loop for thousands of photons. In each run, we generate a random number between 0 and 1 so that we can simulate the discreteness of quantum entities. We then compare that random number r against the calculated probability. If r is less than the probability, the photon passes. The state vector has collapsed to horizontal state. If it's greater, the photon fails, collapsing to the vertical state. By counting the passes and dividing the total number of photons, we get our experimental ratio. In this experiment, we have used 30 degrees of orientation of the filter. On passing 10,000 photons, we get the experimental ratio very close to the theoretical ratio. The blue line is the pure mathematical prediction. The theoretical cos square curve derived entirely from our vector projection and the Bond rule. The red dot are the results of our simulation. Each dot represents the average outcome of 2000 individual quantum mechanical coin flips at a specific angle. The beauty of this graph is undeniable. The chaotic random outcomes of thousands of individual quantum measurements perfectly conform to the elegant, predictable mathematical curve. With our functions defined, we can now run the full simulation. We use the NumPy's lean space function to generate 50 different angles between 0 and 90 degree. For each of those angles, we calculate the theoretical cos square probability and then run 2000 photon simulation. This loop generates two sets of data, the perfectly smooth theoretical curve and the slightly noisy experimentally observed ratios.